Hey guys, this little session is going to be about density and some other things. I'm not going to go in really great detail about this stuff. I'm just going to kind of hit it quick because it kind of tees up going a little bit deeper into a few things that are way more important in terms of aquatic science. My first question here: how does this huge hunk of steel and metal float? Remember, if you took this battleship right here and threw it in water, the materials that it's made of would sink, right? But because we have increased the amount of volume over which those materials are spread, it then has the ability to float. So remember that density is mass divided by volume, right? So if you remember that density is mass divided by volume, then if you have a really small mass and a really big volume, then that's going to be a really small density. So basically whatever you do to volume is inversely proportional to density, and then whatever you do to mass is directly proportional to density. So if we increase the mass, that should increase the density, but then if we increase the volume, that should decrease the density. So if we do that, that's basically density in a nutshell. But what does that do in terms of water and other things? First, we already learned that water is most dense at 4 degrees Celsius. So if that hasn't got beaten into your head yet, it needs to be. Which means that any water that gets below 4 degrees Celsius then becomes less dense than 4 degrees Celsius. So if you imagine, 3 will float on 4, 2 will float on 3, 1 will float on 2, and then 0, which is when it starts freezing, will float on top of that. So that creates ice on top. Now remember, most molecules don't do that. Water's pretty important. It's pretty unique in that it does not do, or it does things that other things don't do. So if, for instance, Earth were full of alcohol, which some people might think that it is, but it's not. If it were full of alcohol, so if you had an alcohol lake, for example, when alcohol freezes, it actually becomes more dense than liquid alcohol. So all of the ice would then sink to the bottom and crush everything, right? So it's actually, and then also the alcohol at top would continue to freeze and sink and freeze and sink, right? So water is actually important in that it freezes on top, which then anything that is below that ice can't get access to the cooling air, and it won't freeze. So it's basically an insulating layer. So you might remember that. Then these thermoclines, we'll talk about these in a little bit more depth later, but basically what happens is as water heats up in a lake, for instance, we kind of looked at this with the density column lab that we did, but you end up with a warm layer on top and a cold layer on bottom. There is this middle transition zone, and you saw it on the video. It was the area that kind of does this when you disturb it, right? It's basically just the area where the temperature changes into that cooler layer, but that actually adds stability to the water column, and then that also keeps warm water on top, cold water on bottom, and so you get kind of an insulating layer that keeps several things that we'll talk about a little bit later in place. And then it also turns into this, or lends itself to this lake and pond turnovers, which allows for nutrients to recycle. We're going to beat that dead horse a little bit later. That'll actually be in the next unit. It also density also lends itself to the states of water. Remember, we talked about these H bonds already. We increase H bonds as we move toward a solid. We decrease H bonds as we move towards a gas. Those H bonds, if you remember, if you had a liquid, those H bonds, when it starts to freeze, they form, and that actually will spread the molecule out, right? So basically, those H bonds are what help create the ability of it to expand as it freezes. As a liquid, water will dissolve a lot of things, and that talks about nutrients or pollutants, Remember, pollutants are hard to get out. Nutrients are things that we need in the water. If it's not liquid, it's not going to dissolve. So we need it to be liquid. So by creating ice on top, that allows nutrients to stay in bottom. It can also allow pollutants to stay in bottom. As a gas, it can be transported in the atmosphere. Obviously, we need water vapor in the atmosphere that's going to create things like humidity and other things. But we also need it to transport from one area to another when we start talking about the water cycle. As a gas, it is going to be less dense than all its other forms, and that allows it to float in air, as it were. And then when it's less dense as a solid, that's basically what I was just saying. Water is most dense at 4. Hopefully that has been beaten into your head. Less dense from 1 to 3, and less dense from 5 to 100 degrees Celsius, and even above 100 degrees Celsius. So why is density important? There's multiple reasons, lots of reasons. So we kind of just talked about all of them. So there's one other density and solution thing that I want to talk about. When solutions form, the density of the solution is going to increase compared to that of pure water. So salt water, for example, when we talk about the ocean, this is kind of an interesting video if it'll play. Let's see, yeah. So this video right here, it's basically a diver right here, and you think that he's in water, but he's still in water. So notice that he is in between two layers. One is a saltwater layer and one is a freshwater layer, and you can kind of see it really well right here below them. You see kind of this, here's a line right here. So you can see as he goes down into the salt water, right, you can see that there's a difference between the two layers. Now what this does the same thing that our temperature differences did, but this one's a little bit more stable, even depending on how salty the water is. But basically this creates stability within that water column. So this basically resists mixing events. If so, this bottom layer gets less disturbed than the top layer would if something were to blow through it, like a wave or wind or something like that, right? So that's relatively important. And then the other thing this does, which we'll talk about a little bit later, is salt water is going to be more dense than, or the saltier water gets, the more dense it becomes, right? So when we talk about the ocean, water, basically at the equator, water is going to evaporate, which is going to leave saltier water behind, which will then start to sink, and that's going to create these areas. We'll get into a little bit more, but they're called downwellings because they move down, right? And then because that density or that dense water is pushing down, it will cause water to rise up in other places, which are called upwellings. So we'll talk a little bit more about those, but you get these downwellings and upwellings, and they're based on density. Same thing happens in lakes, except we call them different things. So we'll get into those a little bit more. But when we do dissolve water, that also does, or dissolve things in water, that also does one other thing. In physics, you probably did the ice cream lab. And if I were to have you here, and I were to ask you what you remember from the ice cream lab, you would be like, "Yay, we made ice cream! Oh, it was so awesome! But my ice cream got salty." So you basically put salt in ice. And then you put the cream and stuff probably in another bag, and then inside that bag, and if your bag broke, then you got salty ice cream, right? But what you didn't realize from that experiment is that whenever we dissolve something in water, it will actually lower the freezing point of water. So ocean water that's salty is actually going to be a lower freezing point than regular water, so it freezes below 0. Why is this important? Well, water can get colder than 0, which means that it won't freeze, right? So it keeps it from freezing. and then it will also raise the boiling point. Now that one's not as important to aquatic environments, but the lowering the freezing point is pretty important. So when you put that salt in that ice, basically what you were doing was you were causing the freezing point of that mixture of ice and salt to become lower temperature. It could get colder and stay colder, and so that allowed you to then freeze cream into ice cream. So in terms of aquatic life, obviously for some things you're going to need to be able to shield yourself from that kind of cold. So for example, if we're talking about Arctic regions where it's really, really cold, and we're talking about ocean environments, you're probably going to need to have a coat, right, when you go in the water. So you'll see things like seals that have, fat blubber stuff that helps insulate them from freezing and getting really cold. So there's probably some more that I'm not thinking of off the top of my head, but notice that whenever we dissolve stuff in water, that lowers the freezing point and it raises the boiling point. So it essentially extends the range over which water is a liquid. And then this is going to be the last thing that we're going to talk about, and this is going to have to do with specific heat. So throw specific heat into your head, and I'm just going to go over this real quickly. Normally, if we were in class, you would do this whole activity where you go and look up these temperatures and whatnot. So I'm taking 3 places. I've got San Francisco, I've got Arizona, and then I've got somewhere over here on the East Coast, North Carolina. Now, if you were to look at the yearly average temperatures, notice that these are all roughly at the same latitude, right? Which means that they should have relatively similar temperatures. But we've got this dude on the West Coast, this dude kind of in the interior, and then this dude way out here on the East Coast, right? And if we looked at the average temperatures of these, the average temperatures in San Francisco, if you've ever been there, people always rave about how beautiful the weather is, right? Anywhere really on the West Coast, everybody raves about how beautiful the weather is. Then when we talk about Phoenix or somewhere in Arizona here, people usually talk about how hot it is. Oh, it's so hot, but it's a dry heat, right? Which somehow that makes it better. 120 dry heat, feels good. Anyway, and then when you come out here, it's usually hot and humid. Very similar temperatures actually to us, a little bit lower, but similar to us. So what's going on here? Like, why does one have such cooler temperatures than say 3 or 2? Well, the big reason for this, and if you're here, I'd draw this out a little bit more, but I'm just going to kind of throw this out there for you, is this big old fat ocean over here. It's called the Pacific Ocean, right? And then there's this smaller ocean over here that's called the Atlantic Ocean. And then right here, there is no water at all, right? So water acts like a thermostat. What is a thermostat? Thermo is heat, stat means stasis or not moving. So basically water helps keep temperature from not moving. And when we're talking about temperature, we're talking about air temperature. So during the day, when the sun is out, we are basically pouring our heat energy into this area to try and heat up the air. But because we are so close to the Pacific Ocean will draw that heat in, and it will basically take the heat from the surrounding air so that the air or land can't heat up as fast, and therefore the temperature stays regulated. So remember, water has a high specific heat. That means if you were to put in lots and lots and lots and lots of heat, the temperature barely changes, right? So the amount of heat that we put in here, San Francisco on the land would start to raise temperature, but the water then starts to absorb some of that temperature, and therefore San Francisco doesn't heat up as much. If we go into the desert, we can see this a little bit better. If we add heat, then everything starts to heat up. There's no water to take that heat away. So you'll see, morning temperatures in the 40s and 50s, and then afternoon temperatures, well over 100 degrees. We're talking Fahrenheit here, by the way. Over here in California, usually the morning is about 60 degrees, the afternoon is about 70 degrees. So 60 to 70, your range of about 10, right? And then here you're 50 to 120, so the range is about 70. And then over here, you're somewhere around the 60s, 70s, and then you're up around the 80s or 90s, right? So you're talking about a 20-degree swing here. And over here, the same thing's going on. You have the Atlantic Ocean, which, if you've ever been to the Pacific Ocean is much larger, so therefore it is much harder to put a lot of energy into and raise the temperature. So the Pacific Ocean is actually quite a bit cooler than the Atlantic Ocean. So the Pacific Ocean basically is not as warm or is cooler. It's somewhere between usually around 70 degrees. So notice that during the morning hours, right, it's around 60 degrees, and in the afternoon it gets up to about 70 degrees. That's because the Pacific Ocean is about that temperature. Over here in the Atlantic Ocean, for talking summertime, the Atlantic Ocean is usually around 85 degrees. So if we start at 70, we can kind of race up to 85, and then from there we can go a little bit warmer, but the water will then start to pull in that heat, right? So here there is no water. It's a desert, and so whatever heat you throw out, everything starts to rise pretty quickly. There's nothing to regulate it. Now, same thing happens at night. At nighttime, the Pacific Ocean is going to release its heat back out into the environment, and that allows it to not cool down as far. So the reason the desert gets so cold at night is because there's no water. So whenever the heat is leaving the land, it's just allowed to leave, and then once it all dissipates, then it begins to cool down even more. Same thing over here in terms of water helping out. The reason the temperatures don't get much below 70 degrees or whatever is because the water around it begins to warm it. So we'll talk a little bit more about that, but that's kind of the basics of this. So remember that water acts as a thermostat and helps keep the heat regulated, stasis, not moving. So balance, right? So it balances our heat for us. If you know that, I think we're in a pretty good spot. We will move forward from here. Look for new installments that build upon these ideas. Until then, we'll talk to you soon.